All right, everybody. We are looking right now at day 2 of our topic 13 notes, and that means we are dealing today with trapezoids. Okay, trapezoids, if you will remember, are a quadrilateral, so that means they've got 4 sides, and two of the sides, as you can see on this example one we've got right here, two of those sides right there and right there are parallel to each other. So those two sides, the ones that are parallel, those are what we call the bases. Okay, so when we look at the area of a trapezoid, what we're going to do is we're going to do 1/2 times the height. Okay, the height is going to be this distance right here in between the bases. Let me see if I can get that pin. Okay, the height is the distance in between the bases. Same thing that's labeled over there to the left, and the base and 1/2 times the height times those two bases added together. Okay, so A and B would be the lengths of these two sides that are parallel to each other. Okay, something you might want to go ahead and add on your paper is that those two things, A and B, those are the lengths of bases. Okay, those are the lengths of the bases. So as we look at this example right here, well, I'm going to look at, first off, the length of our two bases. I'll go ahead and outline those in blue. There's one of the bases right there, 7. One of the bases right here is going to be 10. The other thing that we need is going to be this right here, the height. Okay, so when we're finding the area of a trapezoid, we need 3 things. We need those two bases, those two lines that I drew in blue, and we need the height. So all we got to do is plug those things in. Okay, A and B are the two bases, H is the height, and we plug it all into that formula, and it becomes really, really simple. 1/2 times all of those things. You can simplify it down as you go, but really all you got to do is punch this stuff into the calculator, and we get a total area of 47.6 inches squared. Okay, 47.6 square inches would be the area of that trapezoid. Let's go on now to this next one. Okay, this next one tells us some information right off the bat. First off, one of our bases right up here, one of those bases is 11 feet. We can also see that our height right there in purple, that's going to be 5. So here's the question: what is going on with our other base? Okay, this piece of it down here is 4. This piece of it over here is going to match the top. Okay, that piece right there is going to be 11. So that means our two bases are 11 and 15. Okay, so when we plug all that in, 11 and 15 are your bases, and your height would be that 5 that's given there in the middle. Okay, I understand that some of the notes packet might not match exactly. Okay, I want you to modify it to match the pictures that we have right here on the screen. Okay, the 1/2 times 5 times 26. It's just multiplying all that stuff out. Okay, it does not have to be a whole ordeal. All we're doing is multiplying stuff together, plugging numbers into that formula. All right, so here's the question: in all of this calculation, what's going on with 6 feet right here? And the answer is nothing. Absolutely nothing is going on with 6 feet right there, because that 6 feet, that slant height right there, that is not involved in your calculations. Okay, the only thing that we are interested is these two bases that are marked in blue and the height that's marked in purple. Okay, we don't care about the 6 feet. That is extra information that is designed to throw you off. And if you're doing a multiple choice test, I guarantee you, if this number right here was 6 instead of 5, that would have been one of your answer choices. Okay, and it would have been wrong. So that's how we know. That's what we're looking for in all of this. Okay, that's something you need to watch out for. That's really the only skill, because these formulas are not super complicated, but the diagrams sometimes have extra information like that that's designed to throw you off. So you need to be on the lookout for what is good information and what is not as you look at all your diagrams. Okay, this one right here is a problem that is straight off of last year's DCA. Okay, this is something that is, in my opinion, just an excellent high level example of an excellent high-level example of you cannot go by what the picture looks like. You have to go by what the numbers tell you. Okay, because the numbers tell us that this piece right here is 2. So you would think that this piece right here is also 2, but that's not the case. Okay, this 2 centimeters down here is extra information. You're going to see that it is not involved in our calculations at all. Okay, what I want to draw your attention to right now is this triangle. Okay, I want to draw your attention to that part of it right there. That is what we call a 45, 45, 90 triangle. We know that's the case because this is a right angle, this is 45, and since every triangle always adds up to 180, this one up here has to also be 45. Okay, so since that's a 45, 45, 90 triangle, we know that the 2 legs have to be congruent. So if this part right here is 9, then that means this leg right here is also a length of 9. Okay? When we look at this part right here, since both of these dotted lines represent heights that are dropped straight perpendicular down, that means this piece is 5. And this is the part in particular that really messes people up. Because when you just look at the picture, when you look at nothing but the picture, you could ask yourself, how in the world is it that this piece of the length is 5 and this piece is 9? Okay? That's just what the numbers tell us. Okay? You can't go by what that picture looks like. That we're going by what the math says. So, when we've got all of our when we get all of our values plugged into our formula, we've got one base is 5 up at the top. We've got one base that's 9 plus 5 plus 2, all spread across the whole bottom there, so it's 16. And the height it already gave us was 9. So those are the things we plug in. Okay. After you have all of those numbers, once again, just plugging into the formula, it turns out to be really simple. So that's exactly what we're going to do. We simplify everything down. You can just punch it in the calculator however you need to. Okay, we end up with an area of 94.5 square centimeters in all of that. All right, up next we're going to be talking about how to find the area of a rhombus. Now, y'all may recall that a rhombus, when we talked about categorizing different quadrilaterals earlier on in the year, we said that a rhombus was a specific subcategory of parallelogram. Okay, so if you were trying to find the area of a rhombus, you could just take base times height, just like we did all the other parallelograms. You could do that, okay? But here's the thing. When you're dealing specifically with a rhombus, there are a couple of important things that happen. Number one is that all of these side lengths are the same on a rhombus. The other thing is that when you draw diagonal lines that connect corner to corner, going across like that and going across like that, there's some important stuff that happens. Okay, in those diagonals, the first thing is that they bisect each other. So that means this piece and this piece are the same length. That means this piece and this piece are the same length. Okay, what also happens is that right in the middle where they cross, they are perpendicular. They make right angles. Okay, and because of that, because of all of those pieces being congruent, and because of that right angle, when you draw the diagonals in, when you fully draw those diagonals in, it makes it a bunch of right triangles. And if you mess around with the formula for finding the area of a bunch of right triangles, you eventually get down to this, that the area of a rhombus, based on those diagonals, is the length of the diagonals multiplied together and cut in half. Okay, the way we usually see this, we usually don't see it printed out as 1/2 times diagonal 1 times diagonal 2. We usually see it this way. Diagonal 1 times diagonal 2 over 2. Okay, and that's how we're going to be using it on our problems today. Take a look at this first example. We've got one diagonal in red that is 25 feet. We've got one diagonal in blue that is 22 feet. And when you plug it into that formula, diagonal 1 times diagonal 2 cut in half, You just multiply them together and cut it in half. It does not have to be a whole ordeal, y'all. 275 square feet. Come on over to this next one. This next one is interesting because we got to use some of that knowledge about our diagonals, okay? If this side of it is 4, we know that the diagonals bisect each other. That means they cut each other in half. So if that side is 4, that means this side is also 4, okay? We also know that since there's a right angle right there in the middle, and the hypotenuse of that right triangle. Okay, I'm gonna look at it in terms of this triangle alone for a second. If we've got one leg that's 4 and the hypotenuse is 5, the only way that possibly could work is if this other leg was 3. That's one of our Pythagorean triples, you may remember, a 3, 4, 5 right triangle. And if you don't believe me, plug it into Pythagorean theorem. 3 squared plus 4 squared equals 5 squared, y'all. 9 plus 16 equals 25. It works. It checks out. So that means if this side of it, that also means that if this side of the diagonal is 3, that this side is also 3. So everything all put together, this red diagonal has a length of 6, and our blue diagonal from the beginning right there has a length of 8. So those are the numbers that we're going to plug in. Diagonal 1 times diagonal 2 is 8 times 6. And then we cut it in half. Cut it in half, we get a total of 24 square meters. Go on to our last one right here. Our last one, it tells us some information. It gives us that one side length is 6. Okay, I'm going to look at it again. I'm going to look at it in terms of one triangle at a time. Okay, first off, if this is a 60-degree angle, that means this one is also a 60-degree angle. And if we're dealing with a 60-degree angle and a right angle in this corner, as we always do with the rhombus, that means it's a 30, 60, 90 triangle. If we have a 30, 60, 90 triangle, there's some special relationships that happen in between the side lengths. First is that the shorter leg is half the length of the hypotenuse. So if our hypotenuse is 6, that means this piece right here, that's going to be a length of 3. And since the diagonals bisect each other, this is also going to be a length of 3. So that blue diagonal going all the way across right there is a total of 6. The other special relationship in a 30, 60, 90 triangle is that is between the short leg and the long leg that I just outlined in red. Okay, the short leg and the long leg are related by saying that the longer leg is the short times, okay, long equals the short times square root of 3. Okay, so that means this red piece that I just outlined is 3 times square root of 3. That means this other red piece is also 3 times square root of 3. And when you put them together, all together, that red diagonal is 6 square root of 3. Okay, we did 3 square root of 3 times 2. Okay, we just doubled that length. So we multiply the things that are on the outside. 3 times 2. Those two together give us that 6. We leave the radical alone. So that's our entire red length. Our entire blue length we already knew was 6, and those are the things that we're going to multiply together. Diagonal 1 times diagonal 2 is 6 times 6 square root 3. Okay, once again, you multiply the things that are outside of the radical. 6 times 6 gives us a 36, and we leave that radical alone. Again, we deal with the things outside of the radical. 36 divided by 2 gives us 18. We leave the radical alone. That's how we get to our final answer of 18 square root of 3. Okay, there is one just like this in your assignment, y'all. It is almost exactly the same thing. Okay, same numbers and everything. Don't overthink it. Okay, our very last thing is going to be talking about kites here. Okay, as we talk about kites, we know that kites are a little bit different than a rhombus, but they've got exactly the same formula. Okay, diagonal 1 times diagonal 2, and we cut it in half. So as we look at our example, we ask what's the length of that diagonal. That one I just highlighted, well, it's going to be 9 plus 5, so that length is going to be 14. The other diagonal, let's see if I can get a different color. A diagonal that I just highlighted in pink is going to be a length of 8. Okay, that's because we've got 4 here and we've got 4 right there. Okay, on a kite, this smaller diagonal is cut in half by the larger one. So all things put together, it becomes, we add up those pieces and we've got 14 times 8 as our D1 times D2. We multiply them together, cut it in half. We've got a total area of 56 on our last example problem there. Okay. You've got some assignments coming up. This is what they're going to look like. Okay. Let me give you all a couple of quick hints. Okay. On the review ones, on the review, on those first couple of problems, there's a couple of ways you can do problem number 3. One way you could do it is to look at it as a parallelogram, and then you add the area of a triangle. Or you could just treat the whole thing like one great big old trapezoid. Okay? You could treat the whole thing like one big trapezoid where one base is 40, the other base is 90, and the height is 18. Either way you want to do that, it'll all work out. I believe everything else is going to be pretty straightforward. If you have any questions, just let me know. We'll see if we can figure it out. Okay. Problem number 7 is the one that I was referring to on your notes. Okay. Problem number 7, that's the one that I was talking about that is going to be exactly the same. Okay. So give that one a look over again if you're having trouble. That's all we're going to have for day 3. Y'all have a good one.